Yeah, okay, thanks. Yeah, so yeah, it's exciting to come back to the personal talk for the first time, and I'm happy to introduce Abigail Horn from SUSC actually. So today she's going to talk about her research on tracing the source of large-scale outbreaks of foodborne contamination across complex food supply networks. So Abigail is a research associate in biostatistics, and she obtained her PhD in engineering systems from MIT, and also an undergrad degree in physics from UCSB. And before coming to USC, she completed also a joint postdoctoral fellowship at the Kuhn Logistics University and at the German Federal Institute for Risk Assessment. And the general area of Abigail is the combination of approaches from network and computational social science and systems modeling with large-scale novel data sources to design solutions to pressing public health challenges. Yeah, let's welcome Abigail to give her research talk.
Great, thank you. So I am very excited to be here. It's great to be here in person as well. Should I introduce, there are several upcoming lectures that are so feel free to check the schedule. Here's the first slide of my talk. So I am going to be going over a model-based approach that I've developed to trace the source of large-scale outbreaks of foodborne contamination by leveraging the structure of the complex food supply chain networks that they spread across. Now, before I dive into this main topic, which is going to be the focus of my talk, I want to spend the first few moments giving a bit of a broader overview of my research pipeline and some of the problem areas I'm currently focused on, which I think will help to contextualize this topic that I'm going to talk through and also give a better idea of my approach to research. And that approach is problem-driven. So I choose problems of significant societal impact and develop the tools and methods necessary to approach these problems. So I'm now going to survey several of the areas that I'm currently working in. So one of these areas is the relationship between the physical food environment, this is the spaces where people access food, the food outlets, and eating behaviors. So we know that these food environments impact people's health through the access that they provide to certain types of outlets, the access that they provide, as well as the psychological cues to trigger certain behaviors to visit certain outlets. And so what this means is that if people spend a lot of time in a food environment that looks like the one I'm showing you in the picture here, which is actually the corridor leading up to main campus, they're likely to have a worse overall diet and worse nutritional health outcomes. And so because diet, an unhealthful diet, is the leading risk factor for the chronic diseases that are the leading risk factor for mortality worldwide, anything we can do to impact upon a system level problem by either improving the quality of food outlets in the food environment or the way that people access it can make a major impact on population health. Another of the problem areas that I'm working in is COVID-19 epidemic modeling in relation to health disparities in Los Angeles County, where these health disparities have been greatly exacerbated across the county over the course of the epidemic. And another area that I'm working in and which I'm going to be focused on today is that of identifying the source of large-scale outbreaks of foodborne contamination. So these kind of outbreaks can come through multiple sources. They can come through foodborne pathogens like E. coli or Salmonella that lead to foodborne illnesses, can come through food fraud or food adulteration. So some of you might be aware of the horse meat scandal of 2013. And they can also come through environmental contaminant, so persistent environmental contamination, overuse of pesticides or toxic metals in the food supply. And across all of these problems, we have a common scenario of there's a source somewhere high up in the supply chain, and it diffuses, the contamination diffuses through the supply. And we have the common question of how can we develop approaches to identify the source quickly so that we can mitigate the spread. Now, these are all some of the different types of problem areas that I'm currently working in. And although these are different problems, I use a common set of methods and approaches from data science and mathematical modeling to solve these problems. And these include computational social science, which allows me to represent behavior as it relates to these problems, network science, which allows me to represent structure and relationships in these problems, and stochastic process modeling, which allows me to represent dynamics. As far as data sources, I need data that gives me population scale measurements because I'm dealing with these population scale health and safety challenges. And most recently, I've been drawing primarily from novel data streams, including smartphone geolocation, mobility trace data, application data like nutritional application data, and social media data. I also use traditional, yet still very important, data from epidemiology and transport and logistics. I'm going to spend now the next several minutes doing a succinct deeper dive into each of these problem areas before I finally dive into my main topic. Starting with the relationship between the physical food environment and eating behaviors and ultimately nutritional health outcomes. So the way that this relationship, how food environments impact eating behaviors, the way that that has traditionally been studied in the field of nutritional public health research is to look at people's home neighborhood food environment. And why is this done? It's been done because, of course, the home neighborhood is important to what people eat. People spend a lot of time in their home neighborhood. But it's also, and perhaps moreover, been done because this has been what's been possible to measure. So we know where people live, we can look at the food environment in their home neighborhood, and we can make inferences about how that environment impacts their eating choices and ultimately their nutritional health. But we know this is missing a big part of the picture because at least before COVID, people spent a lot of time outside of their home neighborhood. And I think people are starting to spend more time outside of their home neighborhood again. And in fact, my own research has shown that fewer than 20% of visits to food outlets occur within the home neighborhood. And the fallout of this incomplete measurement is that it's leading to problematic interventions. So over the last 7 years or so, there has been $225 million put into interventions to improve food environments. For example, establishing a grocery store in a neighborhood with low access to that kind of outlet. It's called a food desert. And these interventions have led to basically no measurable impact on dietary changes or ultimately dietary health. And I think that a large part of this is because we're not completely measuring how people access this environment. So my research is trying to move beyond this by leveraging novel data streams and methods from computational social science to measure people's entire day-to-day experience and how they access food environments much more broadly. Specifically, in a large team project that I initiated together with Kayla De La Haye here at USC in the School of Medicine, and Esteban Muro and Sandy Pentland at MIT Media Lab, we're using a data set consisting of millions of geolocations to food outlets and other locations across a user sample of 5 million in 10 major US cities. And this data set gives us this unprecedented perspective into how diverse populations access and use diverse food environments. Some of the research questions that we're investigating with this data include, can mobility data provide a realistic sensor of population eating behaviors? And in fact, this paper that I have cited up here, which is currently under review at JAMA Network Open, shows that not only can it, but it also provides a better predictor of diet-related disease like obesity than self-reported dietary behavior. We're also starting to get at the causal links between food environments and eating behaviors by leveraging the longitudinal nature and the massive scale of the mobility data to design natural experiments, such as when a food outlet is established in a neighborhood and how that changes eating behaviors. Now, I also want to mention that I've experienced developing predictive models of how consumers use food environments, including gravity models. And I'm getting into the area of bringing these kind of models into this nutritional health space because I think this can help inform the design of more optimized interventions to these food environments. Okay, the next area that I'm going to do a little bit of a deeper dive into is COVID-19 epidemic modeling and impact.
Can I ask a quick question, because I know that you're shifting topic.
Yes.
Increasingly more frequently, the food comes to us, right? So the grocery delivery, food delivery services, and so on. How do you think this is going to play out in the future of this problem area? Right now, we have mobility data that allows us to see where people go get their food outside of their, neighborhood environment. But the paradigm shift that is going to happen when people bring food to their home, homes through, whatever is your favorite food delivery services. How do you think this is going to play out?
So I'm actually investigating data from DoorDash and some of these companies, because this is a growing piece of the problem. And of course, over the last 2 years, I think the online delivery services have increased 150%, something like that. So it's a really important part of the problem. Now, a lot of what I'm focused on currently is how do people of lower income access these food environments? And these food delivery services are not as highly used by these populations. So I think for a medium term period, this is this mobility data is still a good window, because smartphone ownership is still, it's 85% over, and there's still good coverage in low income populations, although not complete, of course. So that's a measurement issue as well. But I'm also interested in the whole picture of how it works. And so those kind of data sources are going to be critical to understanding the whole population. Now, where people use delivery services less is during lunchtime visits. And so we can look at, for certain types of eating behaviors or certain times of day, certain data sources will suffice, or others, whereas we need combinations for other times of the day.
Thank you.
Yeah, thanks. Good question. So, and yes, you're right. So I was moving on to the next topic, which was the relationship between, or basically how health disparities have been greatly exacerbated during the COVID epidemic, and how epidemic modeling can help to inform upon that. So I want to start off by saying that my work in this area, the epidemic modeling, has been at multiple levels of engagement, which have included my own research in which I've been leading the epidemic modeling effort out of the Division of Biostatistics in the School of Medicine. But I've also been working with various other stakeholders. So I have worked in collaboration with researchers in the School of Public Policy through my own work, but I've also been working very closely with the Los Angeles County Department of Public Health. And in fact, a lot of the work that I've actually done has been in direct response to requests from the Chief Science Officer at the Health Department. And so that's to say that not all of the research questions I've been asking have come from me, they've come a lot from the Health Department. I've also developed models to help inform USC student health's testing strategy on campus. And so, kind of like I was just saying, working with these different stakeholders has determined my research and also helped to shape the research questions that I've asked when I have been driving my own research. And a lot of my own research has focused on modeling how the epidemic dynamics differ across risk groups within LA County. And so I've been using stochastic epidemic models and multi-population epidemic models that represent the dynamics within and across these different risk groups, where these risk groups can be race ethnicity groups, they can be different age groups, people living in different neighborhoods, people with different health factors, or combinations of all the above. And so these kind of models allow me, when I calibrate models to data that the county is sharing, to estimate how probabilities of getting infected and developing severe illness given infection differ across these different risk strata. And in the paper that I'm citing here, I developed an approach that takes in data, marginal data, on how these probabilities were observed to be affecting specific marginal risk groups like age factor or health factor, and develop a joint probability approach for estimating the combinatorial combinations of people in these different risk groups. And then so I used I estimated those probabilities, and then the next stage was using those probabilities to investigate what if scenarios of different interventions that we could play out in the county. And so a lot of the interventions that I was investigating came from requests from the health department. Okay, so that's what I'm going to say about the epidemic modeling work. And so I'm going to move on. But if you have a question.
So did you have actually information about these different risks groups? Like, did you have information about comorbidities? I imagine you're using some demographic data from census based on tract levels, aggregate levels, but how do you get the other data about their risk factors?
Yes, so we had, first of all, this is population scale. So I was using epidemiological data, readily accessible data. But for the risk factor, the probability of developing severe illness given a risk factor, we were using data that came from early studies on these probabilities. So studies published in the Lancet and New England Journal of Medicine, giving us these hazard ratios and converted into probabilities for the probability of developing severe illness given individual risk factors, right? Given individual health factors or health behaviors like a history of smoking or chronic diseases. And so we had those probabilities from the literature. What we took from, we used another set of data, which was how those kind of risk factors correlate in populations, in the overall population, that we took from, that we estimated from a much larger data set that was a national data set that's called the NHANES study. And so that gave us this baseline understanding of how those
you don't have like neighborhood specific like risk factors in this, okay?
No, we had the neighborhood prevalence of these marginal factors, and then we could estimate, yes, jointly. Good question. Okay, so now I'm getting to the topic I'm going to spend the rest of my talk on, which is that of identifying the source of foodborne contamination. And I'm going to spend a little bit more time motivating this because I want you to understand why it's an important problem to solve, because in the age of COVID, we can kind of lose sight of the importance of other infectious diseases. And so foodborne diseases, and I'm gonna be focused, I talked earlier about multiple sources of foodborne contamination. In the following, I'm going to be focused on foodborne pathogens and those that cause foodborne illnesses like E. coli, salmonella. And the toll of foodborne illness in the US each year is quite large. So there are millions of illnesses and over hundreds of thousand hospitalizations due to foodborne illnesses each year, and billions in healthcare costs, not to mention untold costs of the economy when something goes wrong. And more often than not, when something goes wrong, we're not able to do anything about it because the majority of outbreaks go unsolved, meaning we're never able to identify the source high up in the supply chain. And so we're not able to develop effective measures to mitigate its spread. And for those that are solved, which there are, of course, some that are solved, they're often solved too late. So let me show you what that looks like with a specific example. So the example I'm using is the 2011 outbreak of E. coli carried by contaminated sprouts, later traced back to a farm in northern Germany. This outbreak led to thousands of illnesses and 54 deaths across much of Europe, 16 countries, with the largest burden of disease being in Germany. And it took investigators 6 weeks to identify the source. So let me show you why that was too long by looking at the epidemiological curve. So here's the curve showing the number of cases by date. The outbreak was identified in early May, and 6 weeks later, when the source was identified at a small organic farm in northern Germany, the contamination had already made its way through the supply chain. You can see by the epi curve. So basically, yes?
Like you said outbreak, but if there's very, very few cases, why does it qualify as an outbreak initially?
So that's a good question. That's why I said outbreak was identified. And so that's through the sequencing. So case patients, people get ill with foodborne illnesses and they go to their doctor, and the doctor takes a sample, and that sample gets sequenced. Actually, the technology, this was 2011, the GWAS wasn't as prevalent then, and so at this time there was something called DNA fluorescence, I'm forget, PFDA. There's another technology, took a little bit longer, but it was enough to identify the serotype. And so when you had enough cluster of cases that had the same serotype and presented in an illness from E. coli, it's hemorrhagic, it's E. coli toxin poisoning, essentially. And so they were able to link the strains from those samples together and determine that was
But I'm asking, like, but they didn't know on May 1st or 2nd where you have the error. They didn't know that there was a problem yet, right? This is looking post hoc.
I think the question is about the definition, right? Why was it defined as on May 2nd as an outbreak? Well, I think it's a post hoc definition, right?
Actually, no. So
Well,
the
it
definition of
sounds
an
like
outbreak,
because they have the same genetic source for
From
the
like
disease.
10
so-
people or 5 people?
yeah, the definition of an outbreak is 2 or more cases of the
Okay.
same strain. That's the definition of an outbreak by the CDC.
Okay,
So,
so they really monitor at that level, huh? 1 or 2 people get sick and they monitor it further.
yeah, they might not do anything about it until later. So I think that's where your question is very astute, is in that, yes, we knew it was an outbreak, but it wasn't until the next week, and there were double the number of cases that they maybe started riling up the troops. Okay. So the point that I was trying to make with this slide is that after we did see a lot of cases and the outbreak was being investigated closely and there were investigators in multiple countries, throughout Europe trying to track this down, and Spanish were trying to show that it wasn't a Spanish cucumber which had been implicated, and people who were aware of this outbreak might remember that media sensation. And anyway, by the time that they did identify it, it was too late in terms of the public health impact, because you can see the bulk of the curve had already, most infections had already come about. So, yes.
Quick question. So it just died out by itself because the original batch kind of exhausted, or there was some other?
Yes. So that there weren't mitigation efforts that were directed. So it was eventually traced to these sprouts. There weren't mitigation efforts that were specifically implicating sprouts or sprouts from Germany until this point in June, when it was identified, because it had been limited down to certain kinds of vegetables and salads, but it was very generic. And there's some behavioral shift in that people were eating fewer salads.
Yeah, I was in England at that time. I remember that people were like freaking out and nobody was buying produce, like fresh produce anymore.
Yeah.
So I was wondering whether the outbreak itself, the infections kind of died out because the original batch, let's say, of infected produce ran out, that we ate all of it, and then there is only this many people that can get infected, or if it was reconduced to a temporary change of behavior. Places stopped selling fresh produce, people stopped buying them, and so on.
Yeah, no, so it was a batch that had made its way through, because the batch came through. It was actually the producer of the batch was where I have this organic farm where I have the X in the map, but that batch, it was a batch of seeds that came from a contaminated farm in Egypt. And so once that batch of seeds had been used, the contamination had already.
So let's say in principle, if there were way more seeds and then it took the same time, way more people could have been infected.
Yes.
Just out of curiosity, why are the cases in females so much higher than in males? Does anybody know?
Salads.
Is that it? It's difference in diet?
Yeah.
That'll teach you.
It's not obvious to you?
All right. So good questions here. this is the lead-in to the model-based approach that I'm gonna be explaining now. So motivated by examples like this, and there are other examples like this where there's a large-scale outbreak, there are a lot of investigation efforts focused on it, and by the time the source was identified, it was kind of after the fact. So inspired by these approaches, I wanted to see what kind of model-based approach I could take to this problem with the data available to locate the source, develop an approach to help investigators focus in on locations where the source could have come from and do so with greater accuracy and certainty and speed. And so I took a network theoretic modeling approach, and I developed what I call a joint foodborne contamination source identification model. So this model consists of two parts, which I'm going to be talking through. So the first part is a food supply network model. And this is a model. This is not the fine-grained data on the company supply chains and the connections between these companies, because that is not readily available, or at least it was not to us. And so I developed an approach to model this, and I'm going to talk about that approach. And the second piece is a network source location model. So the idea here is given the supply network, let's embed the source inference problem in that network. When there are cases of illness, we link them to the network of the location where the contaminated food was purchased or consumed, and make inferences from those locations about where the source could have been. So I'm going to be talking about my approach to that part of the problem. And because this is a joint model, I'm going to evaluate it jointly on real-world outbreaks. Specifically, I'm going to look at it in application to the 2011 outbreak of E. coli that I just talked through. So I just want to mention that I've worked on various sub-problems within this area of the contamination identification problem. I'm going to be talking about the two papers that are highlighted here in blue in my talk, but I'd be happy to talk about some of these other approaches later. And so the outline for the rest of my talk is going to follow that joint model structure. So I'm going to first talk through the food supply network model, second, the network source location model, third, its evaluation jointly on the 2011 outbreak, and then I'll close on recent and ongoing work that extends this modeling-based approach. Okay, so for my first postdoc, I applied for and obtained funding to move to Germany to work with Hanno Friedrich, who's a professor of transportation and freight modeling at the Kuhne Logistics University in Hamburg. So Hanno had been developing simulation models of transport demand in food logistics in Germany. And I had identified the simulation framework that he developed and the data in this framework as being able to provide the substrate for developing a network model of the food supply chain in Germany. And so Hanno and I worked together to adapt the simulation model into this network framework that you see here, and that I'm going to be now describing, and which I will later show is usable in source identification. So I'm going to first kind of overview this model. And so in general, it is a multi-layer network, and it's spatially and industrially aggregated. I'm going to break that down now a little bit more. So it is aggregated across these multiple layers, these stages of supply, consisting of production, processing, warehouse consolidation, retail sale, and consumption. And it's spatially aggregated across 402 county-level regions in Germany, with 50 important export country trading partners, 225 individual warehouses, and 30,000 individual retail stores, and consumption at 402 regions, the same county-level regions. And it is also aggregated across these commodity categories. And so these commodity categories are groups of foods that were determined based on the data that we had access to, which I'll talk about a little bit more. And so these included, these categories could be vegetables, and then we look at the flows of raw vegetables that go into vegetable products and vegetable juices and so on. And in total, there are 51 commodity group categories, which again were determined by the data sources that we had available, but together they represent the entire food supply in Germany. So I've talked about the model setup and essentially the network nodes. So again, these 51 commodity group categories, the 5 supply stages, and the 452 regions. And the question is how to estimate the links between these nodes. And so the first part of that is the flows between the commodities. So this is the question of what commodities are required for downstream production of other commodities. And so for this, to answer this part of the question, we sifted through a lot of data, agriculture and industry statistics and production statistics, and came up with essentially this network of which foods are required for production of other foods. And so that was defining this part of the problem, the flows between commodities. The more interesting piece is how we estimated spatially where these links come from. And this is broken down to 2 parts. First, sifting through the data again to identify the volumes, the supply and demand volumes for each supply stage and region and commodity. And then the second piece is using an assortment of model-based approaches to estimate the links that satisfy the supply and demand constraints. So to talk about that a little bit more detail, we again sifted through these various data sources to come up with these supply and demand constraints at each stage. And so this included these data sources I'm listing here, like agriculture and industry statistics, import and export data, and then we had individual data on warehouse locations and retail locations and their revenues and consumption statistics. And I have employment data up here because some of the, for some of the commodities, we didn't have region level supply or demand, production or consumption, and we disaggregated it using assumptions about employment. Not assumptions about employment. We knew the employment and we disaggregated the quantities using those values. And I want to point out here that the way that this was set up, it achieves mass balance, not only for each commodity, but also across combinations of commodities. And this is important. So as an example, take vegetables again. So we know we have data on the amount of vegetables that are produced and the amount of raw vegetables that are imported to Germany. And the sum of those has to equal the amount of the vegetables that are used for downstream processing of vegetable products and so on, plus the amount of vegetables that are exported, and of course, the amount of vegetables that are consumed by the final consumer. And so because we have this term that allows for the usage in processing of other products, this achieves mass balance across all commodities. And so with that, we can use models to estimate the links between each commodity and stage. Yes?
There is no waste assumed in the model, nothing gets thrown away.
So we don't have a waste factor. Yeah, we do have the usage by the final consumer does account for kind of that amount. That is another big issue though in food is food waste. So, pertinent question.
But I'm just not clear. I mean, none of this, like warehouses or grocery stores, none of them act as long-term storage, you know, so can't you just assume like in and out is going to be balanced all the time because it's not going to be, you know, food is not going to stay there for a long time. It will spoil and whatsoever.
Right, but there still will be waste at various points, especially at the point of sale, right? So not all of the food that makes it to the grocery store is going to get purchased. A lot will get thrown out. And so I think that...
Well, I guess what I'm asking more is about like temporal granularity of this modeling. You're trying to get basically daily fluctuations in the volume of food, or are you going to like weekly or what?
Right, okay, so good question. I didn't bring that up at all, the temporal scale. So the way that I developed this from the network perspective is to just get the time average flows. And so it's the daily time average flows. In the original simulation model, is built as a simulation model, and it accounts for weekday and weekend patterns and the differences in temporal scales for storage for different kinds of commodities. And so vegetables, of course, having a much faster supply than
the shelf life.
Yeah. And there's also different temperature ranges as well. So So for getting these time average flows, which is what we're focused on for the network perspective, I break it down into these two parts. First are the links between warehouses and retail outlets, the part that I have circled here. And so these, we don't do anything innovative here. We assume that the warehouses will find the optimal transport scheme to their retail outlets. And so we set this up like the standard transport problem, where we know the amount that each warehouse supplies and that each retailer demands. And we aim to minimize the total transport costs, so the freight miles that these flows are transported across from the freight's transported from the warehouses to the retailers, of course, subject to those supply and demand constraints.
Abigail, is always the distance, the physical distance, or there are other models that account for the transportation cost or the speed, or whatever other factors that you can account when you optimize the transportation model?
Yeah, so there are definitely more complex models that you could use with more factors. We used simply the distance, yeah, the road distance, not the
straight line.
Yeah. But if you were locating if you were trying to determine the optimal transport scheme for your business, you would probably make this part, you build this out a little bit more.
Yeah, I mean, it might not be the shortest path. It might be the fastest or the cheapest.
Yeah.
Especially if you transport produce that spoils, like maybe the shortest path is also the slower because of traffic or because of whatever, or is it the more expensive? So
right.
I can imagine how this can be complexified. I was just trying to understand.
Yeah, what we did, yeah.
Thank you.
Okay, so the next piece then are the links between producers to processors to warehouses. And so this part, I think, is a little bit more interesting, the way that we set this up. So we set up a gravity model for each commodity, and we're trying to estimate with the gravity models the flows between pairs of regions in these subsequent supply stages. And so we know, again, from the supply and demand amount, we know the amount of commodity supplied at the upstream location in a region I, and the amount of commodity demanded at a downstream supply node at a region J. And we're trying to estimate the flow between them. And the basic idea of the gravity model is that the probability that there's a trade relationship and the amount that's traded is proportional to the amount of the commodity supplied, the amount of commodity demanded, and inversely proportional to the distance between them. So it has origins in physical gravity model. And we use the doubly constrained gravity model because we want to satisfy both the supply and demand constraints. And what we know is in black. Again, we know those supply and demand amounts and the distance between regions. And what we're trying to estimate is in red. So we're ultimately trying to get the flows. And the parameter that we're focused on is the distance deterrence factor. So this parameter is telling us, of course, how important is distance to determining this trade relationship. And in just to link this back to the overall problem that we're trying to solve of how to use this in identifying the source of an outbreak. So this parameter is particularly important because it determines how far we could expect a commodity to be distributed from a certain origin location, right? And so as an example of that, I can show the production and supply of several different products in Germany. So on the left, I have sugar beets, and on the right, I have sugar, and I'm showing their production in green and the demand with these orange arrows. And so you can see that sugar beets are produced in many more locations, and they're consumed more locally. And so distance is more important in determining that trade relationship, and the distance deterrence factor will be lower for sugar beets than for sugar. Okay, and so we estimate those betas, those distance deterrence factors, through a joint calibration process. And again, those betas determine the gravity models, which give us our flows across these stages. But the calibration data that we have is freight data, and freight flows across all of these 4 stages. And so we have to calibrate, we have to set up the calibration process across these 4 stages. So let me just tell you a little bit more about this calibration data. So it comes from the German Federal Transport Infrastructure Plan. and it represents all freight flows between pairs of regions aggregated across all commodities and all supply stages. And so basically it gives us this matrix of freight originating in region I and ending in destination J. And so again, aggregated across all commodities and supply stages. And the US equivalent of this data, for those of you that are familiar with this kind of data, is the freight analysis framework out of Oak Ridge National Lab. And so with that, we have everything we need to set up the calibration problem. So what we know is in black, again, the Federal Transport Infrastructure Plan data. And in the middle here, we have these flows between warehouses and retailers that we don't know, but we estimated and we fixed those. We have the transport problem fixed. And what we're still trying to estimate are these flows that come from the gravity models, which are determined by their beta parameters, their distance deterrence factors. And again, we have one of those for each commodity category. And so the form of our objective function is a least squared error, minimizing the least squared error between the sum of all flows across these stages and our observed data, our observed transport freight data. And of course, this is subject to our commodity mass balancing factors, so the supply and demand constraints. And I just want to point out here that this is not a typical loss function setup, because in addition to the constraints that I have written out here on the slide, we have all the additional constraints that are embedded in the way that we set up the problem. So whereas you could look at this as having, this network is having multiple hidden layers in there, we actually enforce the structure of those hidden layers in the way that we set up the model, right? And so we have those embedded constraints in the way that this whole problem has been set up. Okay, so once we have this set up, our goal is to solve it and estimate those betas. And we do this with a grid search. So we discretize the search space and we further restrict it by using our knowledge about the way that foods can be distributed. So we define for each commodity a reasonable, we limit the values that the distance deterrence factor can take on, such that they're reasonable for each commodity based on upper and lower bounds on how far that commodity would be transported. So we set that all up and we solve this problem, and that's what I was going to say about that problem. So then we get our flows. We have all the flows that we need, and we have the network defined. And we can use that in the next stage. So I can move on to the next stage of the talk. And for the next stage, I'm going to be focused on slices of this network. So I'm going to be looking at, for example, the vegetables slice of this network. And so I'm going to talk now about the network source location model. So here's a stylized view of the network that we're just looking at. So again, it still consists of those stages of supply, production, processing, warehouse, and sale. And the source identification problem is the following. So we get reported cases of illness and we link them to the supply network where the contaminated food was purchased or consumed. And the goal is to develop a model that can estimate the probability that any node in this network was the source of the outbreak, and ultimately a maximum a posteriori probability of the source location. I just want to point out that in the following, I'm going to be assuming that the source node is in that first stage of the supply, the production stage. In reality, it can be in any stage, and in the way I set up the model, it can be in any stage in which it can be any node in the network that can reach all of the points that the contamination had been observed, but it's just going to be easier for the purposes of explication to focus on this first stage. Okay, so to formalize this problem a bit more, our objective is to determine the probability that any feasible source in the network is the true source given the observation set, which I'm going to call theta. And so this is a Bayesian inference problem. So we can set it up like one. What is the probability of the source location given the observation set? It's proportional to the prior probability times the likelihood, the probability of the observation set given the source. And that gives us, we can also get our maximum a posteriori, our map estimator of the source location. And the prior probability, it's either given or we could develop a whole other model to estimate it, but for the purposes of the following, I'm going to be focused on how I estimate the likelihood, the probability of the observation set given the source. So let's just assume that the prior probability is given or it's uniform. And so the network source location problem, this has been studied by multiple researchers over the last decade or so. And in this paper that I'm setting down here, my colleague and I reviewed these approaches and discussed why they are mismatched to the foodborne disease problem context. And so one of the reasons for that is that a lot of these approaches assume a contagion dynamics. The contamination is growing as it moves through the supply. But that's not really the case in the food supply. It's kind of back to your question, Emilio. There's this initial contaminated batch, and the question is where that diffuses through the supply. So that's not really necessary for this problem, and or modeling what actually happens. And then another reason why a lot of these approaches don't work is because they cut through the complexity of the network to do the inference problem by assuming the contamination will spread only across the shortest path to the network or the highest probability path. And so clearly the shortest path, that kind of approach won't work in a network where all paths are the same length or approximately the same length. And I can show you an example for why it doesn't work to only look at the highest probability set of paths. So food distribution occurs across multiple candidate paths. And I can give you an example from the 2011 outbreak using our network model. So the source was, I showed earlier, traced back to this farm in northern Germany. And I'm gonna go in my network and look at all the flows, all the links that go from that source to this outbreak cluster in southern Germany. And so I'm showing you here on the right, the top 15 probability paths from that source to the outbreak cluster. And you could, the probabilities of the paths are indicated by the width of the lines. And so you can see that there are a lot of paths of similar probability. So if we're gonna use an approach that just looked at the highest probability path here, we'd be essentially choosing at random from a large number of possible paths. So I want to develop an approach that can account for multiple paths of travel to the network. Yes.
I'm going to ask a very stupid question. Are there foodborne pathogens that cause diseases that are then transmittable by humans?
Yeah, that's not a stupid question. So it depends. So even norovirus, that's the one that can be more transmissible from human to human, but it's still largely food transmittable. But norovirus can be transmitted human to human, but norovirus isn't going to result in a large scale outbreak because it's really it's a local outbreak. It's partly because it's so contagious. But so norovirus is one exception. There can be some oral fecal transmission between household members from an E. coli contamination or salmonella, but that's kind of like second order. Yeah, so it's not as much of a contagion process, although with norovirus being the exception.
So this applies to pretty much the vast majority of foodborne contaminations.
The vast majority of foodborne contaminations that would result in a large scale outbreak. Yeah. So, okay, so good question, not stupid question. So getting back to the problem, so my network model, so a directed weighted network, and I'm not showing it here, but there can be cycles. Now, linking it back, fresh produce, you really won't have cycles. It's gonna move as fast as it can through the supply, but you can for other kinds of products. And the network model allows those cycles. It's not a cyclic graph. And then I've categorized the nodes into transient nodes and absorbing nodes. So of course, the absorbing nodes are the points of consumption. So once it reaches those, it never gets admitted back into the network. And each link in this network is weighted by the relative flows, the relative volumes that we get from the network model. And so I can write the likelihoods back to estimating the source likelihood. I can write the likelihood as the total conditional probabilities over all trees from a source node, from a feasible source node to the observation set theta. And so I'm using this pi symbol, pi s, to represent a single tree from the source to the observation set. And so I'm iterating over all trees where I have to find the probability of a given tree from a source node times the probability, the conditional probability of the observation set given that tree in the source node. And this latter term is simply equal to 1 because given the tree, the observation set's embedded in that tree. So we have that. And so we're really estimating the probability of each tree and iterating over all possible trees from the source of the observation set. And that's a complex problem, right? Because we have to enumerate over all possible trees, and the number of paths from a source to an observation node grows exponentially with the density of the network, and the number of combinations of those paths or trees grows exponentially with the number of observation nodes. So we need to cut through the complexity of the network to solve that problem if I'm not using the quantum computer downstairs. And so the way that I cut through that complexity is to assume independence of the observations. And by assuming independence between observations, I'm also assuming independence between the paths that lead to those observations. And with that, I can show that it's possible to rearrange the likelihood from one that's ordering over all trees from the source to the observation set to one that's ordering over the set of all paths in these independent observations. I'm looking at the set of all paths from an observation, from a source to an observation node. And because these are independent, I can look at those through multiplication. So this is my new likelihood that I'm looking at. And the new challenge is then to estimate the probability of getting from a source node to a feasible source node to the observation node across all possible combinations of paths.
Abigail,
Yes.
Christina, you have about 5 minutes left.
Oh, goodness. Okay. Should I try to finish at that time? Okay. Got so many good questions along the way. So I use Markov chain mechanics, and I can write the dynamics of my process as a Markov process, and I get the Markov transition matrix representing transitions between transient nodes and between transient to absorbing nodes, the other submatrix, and the submatrix representing absorption. And in this Markov process, the transition probabilities are defined in terms of the relative flows out of each, the relative weights out of each node. And with that, I can see the paths to go from a source node to an observation node as an absorbing random walk. And so I have then a nice expression for that, where I have a first term that accounts for all the transmissions between a source node and a node that could lead to the absorbing node, and then the matrix representing the probabilities to go from one of those nodes to being absorbed. So I use that Markov absorbing probability. And I just want to point out that the computational complexity of this has then been reduced down to the limiting factor being matrix inversion, and that's polynomial time. And so I have everything I need, and I have this nice expression for this, what I call the pseudo map estimator, pseudo because I have that independence assumption. And the contribution of this approach is that it, of course, accounts for all possible combinations of paths of travel through the network. And the transmission process has been represented as the diffusion process. And I can show now that it increases the accuracy in the food supply networks, which are not tree-like. And so I'm trying to think about how I use my limited time. I can evaluate it on stylized networks. So I developed these stylized networks that have these kind of practical bounds, these extreme values. One kind of closer to a scale-free network, one closer to a regular lattice, kind of different extremes, but I enforce that layered structure. And I can apply my approach to these networks by simulating outbreaks and tracing them back. And I can also compare my approach to the existing state of the art, which there's only one approach of the existing approaches that could be applied to this problem. And this was the effective distance approach from Helbing and Brockman, which reduces essentially down to estimating, there's a log transform, but practically what it's doing is looking at the highest probability set of paths from a source node to the observation set. And so I can compare my approach to that approach, and in the heterogeneous paths network, where each path has a very different probability than any other path, I can do 10% better than the effective distance approach. But when I look at the homogeneous, the more of the lattice-like structure, I can do way better, because of course, a method that's looking for the highest probability set of paths is going to be choosing at random from a lot of possible paths, whereas my approach can leverage the structure in there. And I just want to show the evaluation on the 2011 outbreak to bring it back home. So again, I'm evaluating the model, the two-part model jointly. And what I'm looking for using the network model is the source region based on those production regions in Germany. And I can trace it back, and I can get the probability mass function over those source regions. And also, you can see the darker shading is higher probabilities. And so as time goes on and cases come in, I'm converging closer on the source. And I can look at the rank of the true source according to my approach. So you can see that already by week 3, the true source location region was ranked in second position out of all 402 regions by the approach. And linking this back to the real world impact. So this was 3 weeks earlier than the investigation was able to resolve it. And you can see that was a large bulk of the infections occurred during that time period. Now, of course, we know that this data was cleaned up, and applying this after the fact is going to look much nicer than applying it in real time. As we know, working with real-time infection data is real messy. But I do want to point out that there is a strong value case for this, and it's actually been implemented and is being used at the German federal level Institute for Risk Assessment, which is the German, if the FDA had a research arm, that's what this institute is. And there's actually a project, an EU project, to apply it in other countries. It's being applied in Moldova right now, so I hope to go there one day. And I can also compare the approach to the evaluation to the effective distance approach, which didn't do poorly on this problem at all, with the main contribution of my approach being that it more consistently and reliably identified the source location. And so I could summarize the results. First, in comparison with the effective distance approach, I was able to do 10% better in those heterogeneous probability path networks, and a lot better, 80% better in the homogeneous, more homogeneous type networks, and a more consistent resolution of the source in real-world outbreaks. But moreover, more generally, in terms of method, because I designed the approach to specifically meet the criteria of this applied problem, I was able to develop this methodological contribution in relation to this problem of an approach that accounts for multiple possible paths of travel through the network. And the network model, it's hard to evaluate how good that is because there's no ground truth. So that's where I think this joint model evaluation gives some indication, it gives some compelling evidence for the value of that network model in being able to identify, provide meaningful information for food contamination modeling and perhaps other applications. So I probably don't have time to get into extensions of this work. I'll just flip through some of this. So I've looked at the problem also of identifying the food item source of an outbreak. So using these model-based approaches to identify the food item source of an outbreak, the idea here is, I see it as a network model comparison problem. So which network model representing different food items out of a set of networks could have most likely supported the outbreak pattern? And so the way that I approach this problem is to look at the information in the probability mass function that comes from tracing back the source, where if there's a lot of structure in that probability mass function, it's an indication that there's some kind of resonance between the network structure and the outbreak pattern. And so I've developed an approach around that. And I've also looked at, I've worked with researchers at the Chinese Institute for Defense Technology. In China, they actually captured this data on supply chain networks that we don't capture here. And so we were able to use that and look at the relationship between features of these networks and the ability to identify the source of an outbreak to kind of indicate some risk scenarios where it's harder to trace back. That's where we might want to invest more investigation efforts or change the supply network structure. I've looked at bringing the time dimension into the problem and an estimator for doing that. But the challenge here is that there's all this uncertainty. There's all these time delays through the supply, the amount of time that it spends at each stage of the supply. And those uncertainties, those variances add, of course. And so we get this very large uncertainty to travel through the supply chain. And so in this paper that I cited here, it's a working paper, but I'm co-advising a PhD student in Germany who's further developing this and showing that there are these very limited scenarios where bringing in that time dimension actually helps to identify the source more than just using the volume-based approach that I was explaining. And we can relax that independence assumption, so different computational methods to approach that. And just to close out, I'm excited about other problem areas that I could extend this to. I mentioned some of these. We can look at both the network source location problem and the food supply network model. And from the network source location problem perspective, there's some of these problem areas that I talked about at the beginning of the talk, like food fraud, food adulteration, where we want to identify the source, and other kinds of diseases where we have a working model of the substrate over which it spreads, a working network model, that is. But then on the food supply network model side, I'm really motivated to apply these kind of methods, the German type method, to the US. And I think there are just a lot of compelling examples for how a model like that could be used in different applications, from the nutritional health examples that I talked about earlier to resilience type questions. I want to acknowledge my funding sources, including a postdoctoral fellowship from the NIH and support from the Robert Wood Johnson Foundation. And of course, my many cross-disciplinary collaborators on all the work I've talked about, the foodborne modeling work, but all of my collaborators. And I'm a strong believer in the importance of team-based science, interdisciplinary team-based science being the way to really make impact and solve these very important societal problems. And so I look forward to continuing that type of work going forward. So thank you, and thanks for all your great questions along the way.